Welcome back to the Deep Dive. Today, we're going to talk about something you could call the elephant in the server room.
A very large, very expensive elephant.
Exactly. Because we spend a lot of time on this show, and honestly, the whole tech world spends all its time talking about how incredibly smart AI is getting. You see the headlines everywhere.
Right. GPT-3, GPT-4, the massive parameter counts.
Yeah, 175 billion parameters, trillions of parameters now. The prevailing narrative is always bigger is better.
It is. The size of the model has basically become the proxy for its intelligence.
Right. But there's this dirty secret in the world of large language models that really doesn't get nearly as much press. And that is, these things are incredibly heavy.
Oh, absolutely.
They're slow.
Yeah.
And computationally, they are astonishingly expensive to run. It's almost like, I don't know, buying a Ferrari that gets 3 inches to gallon and takes 4 days just to start the engine.
That is actually not a bad analogy. I mean, the carbon footprint alone of training these massive models it's comparable to transatlantic flights. It's a very real issue.
So today, for you listening, we are diving into a really fascinating paper from Facebook AI. And it asks a pretty audacious question. Can we put these massive models on a severe diet? Like make them run way faster without making them, well, stupid.
Right. It's the classic engineering trade-off. Usually, if you want speed, you have to sacrifice quality.
Right. You compress a photo, it gets pixelated.
Exactly. You compress audio, it sounds tinny. But this paper, it's titled Linformer Self-Attention with Linear Complexity by Sanong Wang and his colleagues. It suggests that we might actually be able to cheat that trade-off.
And the roadmap for today's deep dive is pretty exciting. We're going to look at why current AI models essentially hit a brick wall when you try to feed them long books or documents.
Bottleneck.
Yeah, the bottleneck. Then we're going to look at this surprising discovery the researchers made about the actual math inside those models. Spoiler alert on that one. A lot of it is just useless noise.
It really is.
And finally, we will break down the Linformer itself, which is the new architecture they built to fix all this.
To really understand the fix, though, we do have to start with the villain of the story, or at least the main bottleneck. And that lies in the very engine of modern AI, which is the transformer.
Right, the transformer architecture. This is the brain behind RoBERTa GPT, basically all the heavy hitters in natural language processing.
Correct. Since about 2017, the transformer has been the absolute gold standard, but it relies on a specific mechanism inside it called self-attention. And while self-attention is brilliant for understanding context, it has a massive flaw when it comes to efficiency.
Okay, let's unpack this. We've used the cocktail party analogy on the show before, but I really want to stress test it today because the math here is usually where people get a bit lost.
It's the best way to visualize it. So imagine a room full of people. Each person represents a word or a token in a sentence. Now, in a standard transformer, for every single person to understand the vibe of the party, the overall context, they have to go shake hands and have a meaningful conversation with every other single person in the room.
Every single one. So if I'm the word bank, I need to go check with the word river to know I'm a river bank. Yeah. And then I need to go check with the word money, just in case I'm a financial bank.
Exactly. And you don't just check with the important words. You have to check with the and is. You check with everyone.
Okay, so if you have 10 people at the party, that's manageable. That's what, 100 interactions?
Roughly, yes. But here's the problem. What happens when you double the guest list to 20 people?
Well, logically, you'd think the work just doubles.
You would think that. But it doesn't. This is what we call the O of n squared bottleneck.
O of n squared.
Yes. If you double the number of words, the sequence length, the amount of computational work actually quadruples.
Quadruples.
Yeah.
Because every new guest has to shake hands with every existing guest.
Plus all the other new guests.
Exactly.
This grows quadratically.
Okay, let's scale this up. Because 20 people is absolutely nothing. A standard AI model input might be 512 tokens, right?
Right. So imagine a party with 512 people. That is over 260,000 handshakes. Now imagine you want the AI to read a whole book, let's say 60,000 words.
Oh, wow.
60,000 times 60,000. We're talking about 3.6 billion interactions.
Just for one layer.
Just for one layer. And these models have dozens of layers.
This is just absurd.
It becomes computationally impossible very, very quickly. The paper actually mentions that training the original BERT large model takes 4 days on 16 cloud TPUs. And that is just for standard short sequence lengths. If you tried to feed it a whole novel at once, the memory requirements would literally just crash the system.
So that's the wall we're hitting. We want AI to read whole novels or analyze high-resolution images or look at long strands of DNA code. But the handshake math, that huge n by n matrix is just way too expensive. It explodes.
Precisely. That matrix, the record of all those handshakes, is the bottleneck. We call it the self-attention matrix. And for years, the field just assumed this was basically the price of admission for getting high intelligence.
But here is where it gets really interesting for me. The researchers at Facebook AI didn't just accept that massive bill. They essentially did an audit. They looked at these giant attention matrices inside pre-trained models like RoBERTa and asked, do we actually need all this?
Right. They performed what's called a spectrum analysis.
Okay.
Essentially, they looked at the mathematical properties of that giant self-attention matrix after the model was completely trained, and they found something that changes everything. They discovered that the matrix is low rank.
Low rank. Now, to me, that sounds like a military insult. Like private, you are low rank. But in linear algebra, that means something very specific.
It does. Let's go back to our cocktail party for a second.
Okay, I'm at the party. 60,000 people, 3.6 billion handshakes. My hand is getting tired.
Right. Now imagine you secretly record every single one of those conversations. What the researchers found is that the vast majority of those conversations are completely redundant.
Redundant how? Like they're just saying the same thing over and over?
Pretty much. It turns out if Bank talks to River, that is important information. But when Bank talks to the or AOR, where the information gained is negligible, or more accurately, the information is repetitive, it's just noise.
So even though everyone is talking to everyone, the actual unique information in the room is coming from a very small group of people.
Bingo. In linear algebra terms, we look at the singular values of the matrix. If a matrix is full rank, every row and column adds something new. If it's low rank, it means you can delete a huge chunk of the rows and columns and you'd still have basically the exact same matrix.
So the overall vibe of the party isn't determined by 60,000 people. It's determined by maybe a few hundred influencers.
Exactly. The researchers plotted this on a heat map, and you can actually see it in the paper. The distribution of information is a long tail. You have a few steep values at the very start, and then a long flat line of basically zero.
So we have these massive, wildly expensive models essentially running around doing busy work. They're shaking hands with thousands of people who have absolutely nothing to say.
That's a very fair characterization. The trained model is effectively screaming, I don't need all this data to understand what's happening.
Okay, so that is the huge insight. The matrix is mostly empty calories. But knowing that is one thing. How do you actually build a model that takes advantage of it? Because you don't know which handshakes are important until you actually do them right.
That is the tricky part, yes. You can't just pick random words to ignore, so enter the Linformer.
The Linformer.
Instead of forcing everyone to shake hands with everyone, that huge n by n matrix, the Linformer uses a technique called linear projection.
Projections. Break that down for us. And keep me at the party if you can.
Okay, I'll try. Imagine that instead of shaking hands with 60,000 people individually, everyone in the room agrees to project their information onto a smaller committee. Let's say a committee of 256 representatives.
A committee. Okay, so I don't talk to the other 59,999 guests. I just talk to the committee.
In a way, yes. The researchers take the key and value matrices, which normally have the full sequence length n, and they multiply them by a projection matrix to squash them down to a fixed smaller dimension called k.
And k is the size of the committee.
Exactly. And here's the real magic trick. K is a constant number. In the paper, they use values like k equals 256.
Wait, so whether the input text is 500 words or 60,000 words, the internal dimension k stays at 256.
It stays completely fixed at 256.
That seems incredibly aggressive. You're taking an entire novel and squashing it into a pamphlet.
You are. But because of the math, the computational complexity goes from O of n squared down to O of nk. And since k is fixed and very small, the complexity effectively becomes linear O of n, hence the name Linformer, linear transformer.
That is a massive difference. If you double the input, the work only doubles instead of quadrupling.
It completely changes the fundamental economics of running the model.
But I have to play the skeptic here for a minute. I'm thinking about compression in the real world. When I zip a photo, it gets a little pixelated. When I stream a movie on bad Wi-Fi, the faces get blurry. You're telling me we can take a massive AI brain, compress its attention span by 99%, and it doesn't get dumber? That sounds a bit too good to be true.
It does sound like magic, I admit. And honestly, if there wasn't rigorous math to back it up, I wouldn't believe it either. But the paper relies on a very famous theorem called the Johnson-Linden-Strauss lemma.
The Johnson-Linden-Strauss lemma. Try saying that 5 times fast.
I will absolutely not attempt that.
What does it actually mean? Without the Greek letters, if possible.
Think of it like a shadow.
Right.
Imagine you have a complex 3D object, like a statue floating in the air. That is your high-dimensional data. Now you shine a light on it and cast a shadow onto the floor. The floor is 2D. You have lost a dimension.
Okay, I'm with you.
But if you cast a shadow correctly, you can still tell how far apart the statue's hand is from its foot just by looking at the shadow. The relative distances are preserved.
So the overall structure remains, even though the fine detail is compressed.
Exactly. The lemma mathematically guarantees that if you project high-dimensional data into a lower-dimensional space, randomly the relative distances between points, the relationships are preserved with very little error.
So the committee at our cocktail party isn't just a random group of people. It's a shadow that perfectly captures the complex relationships of the whole room.
That is the idea. So theoretically, the model can still learn the overall context without needing the full high-resolution handshake list.
Okay, I buy the math on paper.
Mm?
But the researchers didn't just stop there. And this is the part where I actually got a little confused and frankly a little suspicious. They started experimenting with sharing these projection matrices.
Oh, this was easily the most shocking part of the paper for me.
They call it layer-wise sharing. Can you explain what they actually did?
So remember the projection matrix, the lens or the flashlight that creates the shadow committee? Usually a transformer has many layers, like 12 or 24 layers stacked on top of each other. And usually each layer has its own unique parameters. Layer 1 looks for basic grammar, layer 2 looks for phrases, and by layer 12 you're looking for complex themes or irony.
It's a hierarchy. You build up complexity as you go deeper.
Exactly. So you would naturally assume that each layer needs a totally different lens to look at the data. You need reading glasses for the first layer and maybe a telescope for the last layer.
Makes total sense.
But the researchers tried using the exact same projection matrix for every single layer.
Wait, stop. You're saying the glasses used to read a raw pixel or a basic word are the exact same glasses used to understand a complex emotion 12 layers later?
Yes, a single universal projection matrix for the entire model.
That shouldn't work. I mean, that breaks everything we know about feature hierarchy in deep learning. If I use the same map for the territory at every single level of zoom, I should get completely lost.
You really should. And yet it worked. The results showed that layer-wise sharing performed just as well, and in some cases, even better than having unique matrices for every layer.
How is that even possible?
It implies something really profound about the fundamental structure of language data. It suggests that the compression mechanism, the way we filter out noise, is universal. The noise looks exactly the same whether you're analyzing basic grammar or high-level philosophy.
That is wild. It's like finding out you can use the exact same key to open every single door in a skyscraper.
And practically speaking, it is a huge win because it drastically reduces the number of parameters. You don't need to store 12 different massive matrices in memory. You just store one. It makes the model so much lighter.
So we've got a linear model, we've got shared parameters, we've got a committee instead of a crowded room. It sounds amazing on paper. But as we always say on the deep dive, show me the results. Did they actually build it and test it, or is this just a really elegant theory?
Oh, they built it. They pre-trained a Linformer from scratch on the standard datasets, book corpus, and Wikipedia, just like they did for the original BERT and RoBERTa models.
Did the 99% compression make it dumber?
The perplexity, which is basically a metric of how confused the model is when trying to predict the next word, was nearly identical to the standard transformer.
So no real loss in intelligence.
Virtually none. And then they tested it on downstream tasks. Real jobs like sentiment analysis on IMDB movie reviews or natural language inference tasks like GLUE and IMDB. At a projection dimension of k equals 256, the Linformer actually performed slightly better than RoBERTa base on some of those tasks.
See, that's the part I struggle with. We are doing a fraction of the math and somehow getting better results.
It goes right back to the concept of noise. Sometimes having too much information is actually a bad thing. By forcing the model to look at the committee rather than the whole chaotic room, you might be filtering out the distractions. You're essentially forcing it to focus only on the strong signal.
Okay, but the headline promise here was speed. We wanted to break the O of n squared speed limit. How fast is this thing in reality?
This is where the big win happens. For short sequences, like 512 words, it's about 1.5 times faster, which is nice, but it's not exactly earth-shattering.
Sure, 1.5x is a nice optimization, but it's not a revolution.
But remember, the true benefit is linear scaling. So where it really shines is on long sequences. They tested it at a sequence length of 65,536 tokens.
65,000, that's a small novel. That's basically the Great Gatsby.
At that length, the Linformer is 20 times faster than a standard transformer.
20 times.
Yes,
Yeah.
20 times faster. And perhaps more importantly, because it's not calculating that giant n by n matrix, it doesn't eat up all your system memory or RAM, which means you can use much, much larger batch sizes during training.
This changes who can actually afford to use these things.
Exactly. This is the big democratization angle.
Right.
Right now, if you want to train a model on really long documents, you need a massive cluster of TPUs that costs thousands of dollars an hour.
Right. It's a game strictly for Google and Facebook and OpenAI.
But if the complexity is linear, suddenly a grad student with a decent gaming laptop can actually start playing around with long sequence models. You literally don't need a supercomputer to have an AI read a book anymore.
That is a huge shift for the industry. It takes the power out of the hands of the few and spreads it out.
And it opens up totally new frontiers. Previously, if you wanted a transformer to analyze a high-resolution image or a very long legal contract, you had to chop it up into little pieces because of that quadratic limit. You lost the global context.
Right. The model couldn't remember page 1 by the time it finally got to page 50.
Exactly. With linear complexity, you can feed the whole document in at once. The model can see the connection between the very first sentence and the very last sentence instantly. It fundamentally changes what kinds of problems we can solve with AI.
I imagine this also helps quite a bit with the energy problem we mentioned at the top of the show.
Whoa, significantly. If a task runs 20 times faster, that is roughly 1/20th of the power consumption for that specific inference pass. In a world where AI is consuming city-sized amounts of electricity, linear complexity is basically a green initiative in itself.
It's making the engine more fuel efficient, not just strapping a bigger gas tank to it.
Precisely. The authors actually note in their ethical check that there aren't immediate negative impacts beyond standard deep learning concerns. The whole focus really is just on efficiency and accessibility.
So let's wrap this up for everyone listening. We started with the idea that modern AI is kind of bloated. It's overcalculating. It's essentially shaking hands with millions of people who have absolutely nothing to say.
Right.
We looked at the Linformer, which proves that self-attention is low rank, meaning most of that heavy calculation is just repetitive noise. And by using linear projections, creating that shadow committee we talked about, they squashed the math from quadratic down to linear.
And they did it with the universal lens. That layer-wise sharing proves that the internal structure of attention is much simpler than we ever thought.
Resulting in a model that is 20 times faster at reading books, essentially democratizing access to long-context AI.
That is the perfect summary. It's a real triumph of realizing that more isn't always better. Sometimes smarter is just better.
And that brings me to a thought I've been kind of mulling over while listening to you explain all this. The paper proves that in these massive artificial brains, 99% of the attention is just empty noise. And you can filter it out and still understand everything perfectly.
It definitely seems so.
It makes me wonder, is human attention low rank too? Think about it. We call it zoning out when we stop listening to every single detail in a long meeting. But maybe we aren't really zoning out. Maybe we're just being Linformers.
That is a really fascinating parallel, actually. Our brains are incredibly efficient, mostly because they ignore almost everything around us. We automatically filter out the hum of the fridge, the traffic outside the pattern on the rug. We only focus on the singular values, the sudden threats, the faces, the key words in a conversation.
Exactly. Maybe the secret to high intelligence isn't how much raw data you can process, but how much you can successfully ignore. Maybe laziness is just actimal engineering.
Well, I'm not sure I'd go so far as to call it laziness, but it's certainly highly efficient resource allocation. If the Linformer teaches us anything, it's that knowing what not to pay attention to is just as powerful as paying attention.
I am definitely going to tell my boss that the next time he catches me staring out the window. I'll just say I'm not daydreaming. I'm just optimizing my projection matrix.
You'll have to let me know how that goes over.
I will report back. But that is all the time we have for today's deep dive. Thanks so much for listening, and we'll catch you on the next one.